Today we are going to learn about transfer learning for image classification, a practical guide. You will discover how to apply transfer learning to boost model performance and gain practical skills in implementing transfer learning for image classification tasks.
Welcome to this video on transfer learning for image classification. Transfer learning is a powerful technique in machine learning where a model developed for a particular task is reused as a starting point for a model on a second task. The main advantage of this approach is that it leverages previously learned patterns from large datasets, which are often difficult and costly to acquire. In this video, we'll explore how transfer learning can significantly boost the performance of image classification models. We'll uncover how you can reduce the need for large datasets by utilizing pre-trained models like VGG16 and ResNet. By the end of this session, you'll have practical skills in implementing transfer learning for your own image classification tasks. Let's dive in. Transfer learning involves taking a pre-trained model and adapting it to perform a different but related task. This approach is particularly useful in image classification, where gathering and labeling large datasets can be prohibitive. By using transfer learning, we can leverage models that have been trained on vast datasets like ImageNet, which contains millions of images across 1,000 categories. This practice allows us to use the knowledge these models have gained, applying it to our specific problem with minimal additional data. The primary advantage of transfer learning is efficiency. Instead of training a model from scratch, which requires substantial computational resources and time, transfer learning allows us to start with a model that already understands visual features. We then fine-tune it to recognize classes relevant to our task. This process involves a few key steps: selecting a suitable pre-trained model, modifying the architecture to fit our new task, and retraining it with a smaller, task-specific dataset. This strategy not only saves time but also improves the model's performance by building on a solid foundation of learned features. When it comes to transfer learning for image classification, two of the most popular pre-trained models are VGG16 and ResNet. VGG16, developed by the Visual Graphics Group from Oxford, is known for its simplicity and depth. It consists of 16 layers and is praised for its performance in image classification tasks. On the other hand, ResNet, short for residual networks, introduced by Microsoft Research, employs skip connections or shortcuts to jump over some layers. This architecture allows for the training of much deeper networks, such as ResNet 50, which has 50 layers. The key difference between VGG16 and ResNet is in their architectural complexity and depth. VGG16 is straightforward but requires more parameters, whereas ResNet is more complex but efficient in training deeper networks. The choice between these models depends on your specific needs and computational resources. If your task requires recognizing fine-grained features with a simpler architecture, VGG16 might be suitable. However, if you need to leverage a deeper model with innovative architecture to capture more complex patterns, ResNet is a better choice. Understanding these models' strengths and limitations is crucial in selecting the right pre-trained model for your task, optimizing both performance and efficiency. Selecting the right pre-trained model for your image classification task involves several considerations. First, evaluate the size and complexity of your dataset. If you have a smaller dataset with fewer categories, a model like VGG16, which requires a more straightforward architecture, may suffice. However, for larger datasets with intricate patterns, a deeper model like ResNet might be necessary to capture the complexity. Next, consider your hardware constraints. Deeper models like ResNet require more computational power and memory. If you're limited in these resources, you may need to opt for a less demanding model or utilize cloud-based solutions for training. Additionally, consider the specific requirements of your task. If your task involves identifying very subtle differences between classes, a deeper model with more layers could be beneficial. However, if the classes are more distinct, a simpler model might perform equally well. Finally, it's essential to balance accuracy and efficiency. While deeper models can potentially offer higher accuracy, they also consume more resources. Therefore, it's crucial to align the model's capabilities with your project's goals and constraints, ensuring you achieve the desired performance without unnecessary resource expenditure. Keras, a high-level neural networks API, is an excellent tool for implementing transfer learning. It provides a user-friendly interface to load and modify pre-trained models. To start, you'll need to import the necessary libraries, including TensorFlow and Keras. Next, load a pre-trained model, such as VGG16 or ResNet, using Keras built-in functions. These models are available with weights trained on large datasets like ImageNet. Once the model is loaded, you'll need to modify its architecture to suit your specific task. This adjustment typically involves replacing the final layer with one that matches the number of classes in your dataset. For example, if you're classifying images into 5 categories, the output layer should have 5 nodes with a softmax activation function. After modifying the architecture, prepare your dataset for training. This preparation involves resizing images to match the input size required by the model and splitting the dataset into training and validation sets. With the dataset ready, train the model using the adjusted architecture. Keras makes this process straightforward with its fit function, allowing you to specify the number of epochs, batch size, and validation data. Finally, evaluate the model's performance using metrics such as accuracy and loss on the validation set. Keras provides built-in functions to easily assess these metrics, giving you insights into the model's effectiveness in classifying the new data.
Fine-tuning is a critical step in optimizing the performance of a transfer learning model. It involves selectively retraining some layers of the pre-trained model to better adapt to the new task. This process can significantly improve accuracy, especially if the new task is similar but not identical to the original one. Fine-tuning is particularly useful when the dataset is large enough to warrant further training beyond the pre-trained weights. To start fine-tuning, you'll need to decide which layers to retrain. Typically, the earlier layers capture general features like edges and textures, while the later layers focus on more task-specific patterns. Therefore, it's common to freeze the earlier layers, maintaining their weights, and retrain the later layers. Adjusting the learning rate is another crucial aspect of fine-tuning. A smaller learning rate is recommended to prevent drastic changes in the pre-trained weights, allowing the model to adapt slowly and effectively. Keras makes it easy to implement these adjustments with its flexible layer freezing and optimizer configuration options. Fine-tuning can significantly enhance the model's performance, making it more robust and accurate for the new dataset. However, it's essential to monitor the model's performance during training to avoid overfitting, ensuring that the model generalizes well to new, unseen data. Let's walk through a practical example of using transfer learning for image classification. We'll use Keras to classify a dataset of images into several categories. First, set up your environment by installing the necessary libraries, including TensorFlow and Keras. Ensure you have a compatible GPU to speed up the training process. Next, load and prepare your dataset. This step involves organizing your images into directories based on their categories and resizing them to match the input size required by the pre-trained model. Once your data is ready, load a pre-trained model like VGG16, excluding its top layers, and add a new output layer that matches the number of categories in your dataset. Compile the model with an appropriate optimizer and loss function, typically categorical cross-entropy for multi-class classification tasks. With the model configured, train it on your dataset, specifying the number of epochs and batch size. Monitor the training process using Keras built-in callbacks, such as early stopping and model checkpoints, to handle overfitting and save the best performing model. After training, evaluate the model's performance on a validation set to check its accuracy and adjust any hyperparameters if necessary. Finally, interpret the results to understand how well the model generalizes to new data. This practical example demonstrates the power of transfer learning in building efficient and accurate image classification models with minimal effort. While transfer learning offers significant advantages, it's essential to be aware of common pitfalls that can hinder model performance. One major issue is overfitting, particularly when working with small datasets. Because pre-trained models are often complex and have many parameters, they can quickly memorize the training data rather than learn general patterns. To combat overfitting, apply techniques such as data augmentation, which artificially expands the dataset by applying transformations like rotation and flipping. Another common mistake is choosing the wrong pre-trained model for the task at hand. Not all models are suitable for all tasks, and selecting an inappropriate model can lead to suboptimal performance. Ensure the chosen model aligns with the complexity and characteristics of your dataset. Ignoring data augmentation is another pitfall. Data augmentation can significantly enhance model robustness by exposing it to a variety of input scenarios, making it more adaptable to real-world data. Inadequate fine-tuning can also be detrimental. Simply using a pre-trained model without adjusting layers or learning rates can result in poor adaptation to the new task. Proper fine-tuning helps the model better capture the nuances of the new dataset. Lastly, misinterpreting evaluation metrics can lead to incorrect conclusions about model performance. It's crucial to understand the metrics used and ensure they align with the task's objectives, providing an accurate assessment of how well the model will perform in practical applications. The field of transfer learning and computer vision is rapidly evolving, with several trends shaping its future. One significant trend is the advancement in model architectures. Researchers are continually developing more sophisticated models that achieve higher accuracy with fewer parameters, making them more efficient and accessible. Another trend is the increased efficiency in training. Techniques such as model pruning and quantization are helping reduce model size and computational requirements, allowing for faster and more cost-effective training processes. Transfer learning is also expanding its application across diverse fields beyond traditional image classification. From medical imaging to autonomous vehicles, transfer learning is finding utility in various domains, leveraging pre-trained models to solve complex problems with limited data. Integration with unsupervised learning is another promising direction. Combining transfer learning with unsupervised techniques can enhance model performance, enabling it to learn from unlabeled data and discover hidden patterns. This integration has the potential to significantly improve the model's ability to generalize across different tasks. Finally, emerging research directions are exploring areas like meta-learning and few-shot learning, which aim to create models that can quickly adapt to new tasks with minimal data. These advancements promise to further enhance the capabilities of transfer learning, making it an even more powerful tool in the field of computer vision.
As we conclude this video on transfer learning for image classification, let's recap the key points we've covered. Transfer learning offers substantial benefits, such as reducing the need for large datasets and accelerating model development. We've explored the essential steps in implementing transfer learning, from selecting a pre-trained model to fine-tuning it for your specific task. Understanding the importance of model selection and fine-tuning is crucial for optimizing performance and achieving accurate results. We've also highlighted common pitfalls, such as overfitting and choosing the wrong model, and how to avoid them. Looking ahead, the future of transfer learning is bright, with advancements in model architectures and increased efficiency promising even greater applications in computer vision and beyond. We hope this practical guide has equipped you with the knowledge and skills needed to effectively apply transfer learning in your projects. Thank you for watching, and happy learning!